Hi there, welcome to my channel. In this video, I am going to discuss about the solution for finding the regions that are surrounded. Let's look at the problem description. We are given a m by n matrix board containing letters x and o. We have to capture the regions that are surrounded. A cell is connected to adjacent cells horizontally and vertically. So basically this cell is connected top and bottom and then left and right cells. And to form a region, connect every cell with value O. So this is a connected region. The region is surrounded with X cells if you can connect the region with X cells and none of the region cells are on the edge. For example, this region is connected with X in all the side and it is not on the edge of the board. So we can capture this. But this cell is the only cell in the region and that is also on the edge of the board. So we cannot capture this region. And to capture the surrounded region, we have to replace all the O's with X. So once we determine this region is surrounded by only X and not on the edge, we have to fill all the cells with value X. And we have to do this in place within the original board. Let's take a look at the example 1. These three cells are surrounded by X. So we can capture these three cells and update those cells value with X. But this cell is on the edge of the board, so we cannot capture that cell. So in this case, there is only one cell, so there is no change in the output. The constraints for this problem are m is equal to the number of rows in the board, n is equal to the number of columns in the board. And the row size and column size is ranging from 1 to 200. And the board cells will have value either X or O. We are given a 4 by 4 matrix. In this, there are 4 cells with value O. We have to capture those cells if they are surrounded by X. So in this case, these 3 cells are surrounded by X. So we can capture this region. But this cell is on the edge of the board. We cannot capture this. That's why the value remains same. Basically, we can view this problem as a graph problem. For example, let's take a look at this 8 by 8 matrix. We can view the regions that needs to be captured as a graph. But in this case, the vertices in the graph are all not connected. Multiple components in the graph. So this is one component, this is one, this is one, this is one. Basically, we have to do a graph traversal on this graph. Because it is not connected, we have to do multiple traversal. One for this component, one for this component, one for this, one for this. At the end of each traversal, we need to check whether one of the vertices in that component is on the edge of the graph. So in this case, this region is surrounded by value X. None of this component cells are on the edge of the graph. So we can capture this region. But in this case, these two cells are on the edge of the board. So we cannot capture this. And similarly, this component, this is surrounded by X. And none of the vertices are on the edge of the board. So we can capture this region. But in this case, this cell is on the edge of the board. So we cannot capture this region. Okay. Basically, we have to do multiple breadth first search traversal. At the end of each traversal, we have to check any cells are on the edge of the board. If so, ignore it. Otherwise, mark all the vertices of that component with value X. We have to repeat this until we traverse all the vertices in the board. So that's what I have written here. So we can model the regions to be captured as a graph with multiple components. And each cell in the grid is a vertex. So each one is a vertex and it is connected to the neighbor cells vertically and horizontally. Okay. To capture the region, we have to do the breadth first search on each component. At the end of each traversal, capture the visited cells if none of them on the edge of the board. Okay. Let's look at the flowchart. Input for this procedure is a board m by n matrix. First, we initialize the rows and columns with the number of rows and number of columns in that matrix. And then we create a visited 2D array to keep track of which cells are visited and not visited. Then we traverse the cells in the board and check whether that particular cell is already visited or not. If it is not visited and also it is not captured, then we have to initiate the breadth first traversal from that cell. So we have to repeat that until we process all the cells in the matrix. So let's look at the BFS. Input for this procedure is the m by n matrix board and then the visited array and starting vertex for this traversal. Okay. So first we initialize the queue and the region slices with the starting vertex and then initialize the edge with value false and mark the current vertex as visited. Then we enter the outer for loop. This runs as long as there is an element in the queue. So if the queue is not empty, then we go ahead and dequeue the current element from the queue and enqueue that to the region list. Basically we accumulate the nodes visited in this traversal in the regions list, and for that current node we have to get all the neighbor vertices and then we process all the neighbors by checking whether they are already visited or not. If they are not visited, then mark it as visited and add it to the queue and repeat this until we process all the neighbors of the current node. Once this is done, then we again come back to the outer loop and again we dequeue the head of the queue and then enqueue that to the region. We repeat this until the queue becomes empty. That means all the connected vertices are all visited, and then we check whether the edge is false. In the get adjacency list function, we have to check whether the current cell is on the edge. Okay, in that case we have to set it to true. So if it is still false, that means all the vertices so far visited in this traversal is not on the edge of the board. So in that case we can capture the vertices in the regions list by setting the value captured. Let's move on to coding. First I define the structure for the vertex. Then I define a constant for the visited status. Visited is 1 and not visited is 0. Next I define a constant for captured and not captured state. Then in the solve function, first I initialize the rows and columns and initialize the visited slice of int to keep track of which cells are visited. Then I write the for loop to traverse the cells in the board. If the cell is not captured and also not visited, then I initiate the BFS traversal. I call the BFS function with the board and the visited slice and then the vertex for the current cell. Next I'm going to write the BFS function. First I initialize the queue with the current vertex and then I initialize the region empty slice of vertex. Then I initialize the edge boolean with value false. Then I mark the current vertex as visited. Then I write the for loop which processes all the elements in the queue. In each iteration it dequeue the head, add the current node to the region list. Basically we maintain a list of vertices that are visited during this BFS traversal. Next I call the get adjacency list function to get the neighbors of the current node. The get adjacency list takes the board and the current and then the address of the edge boolean. Next I write a for loop to process all the neighbors returned by the get adjacency list. If the neighbor is not visited, then I add that to the queue and mark that as visited. After the traversal is done, finally I check whether the edge is false. If this is false, that means none of the vertices visited so far is on the edge of the board. So we have to mark all the nodes in the region list as captured. I update each cell with value captured. Next I write the get adjacency list function. First I define the distance slice of int. Basically this contains all the offset value of the neighbors for a given cell. Okay, so this is 1 comma 0 is for the neighbor present in the next row, and minus 1 comma 0 for the neighbor present in the row 1 above. 0 comma 1 is for the next column, and 0 comma minus 1 is for the previous column neighbor. Then I initialize the adjacency list. Next I write the for loop to traverse distance slice. Each iteration I compute the row and column index for each neighbor cell by adding the offset values, and then I check whether the neighbor cell indexes are out of bound. If it is out of bound, that means the current cell is on the edge of the board. So I mark the edge boolean as true and then continue. Otherwise, I check whether the neighbor is not captured yet. If it is not captured, I add that to the adjacency list. Finally, I return the adjacency list. Next, I am going to run the test cases. Typo. All the tests passed. Next, I am going to submit this program. Cool, this program is accepted. Next, I am going to do the code walkthrough with sample input. We are given this 4x4 matrix, and in this there are 4 cells that are with value O. We have to capture those 4 cells if possible. Okay, so in this case 3 cells are surrounded by X, so we capture those 3 cells, but this cell is on the edge of the board, so we cannot capture that. That's why it remains O. Okay, so first we initialize the rows and columns variable. So the number of rows is 4, columns is 4. Okay, next we initialize the visited slice of int. Then we enter this for loop. Okay, so this for loop initiate the breadth first search only if the cell is not captured and the cell is not visited yet. Okay, when we begin, all are initialized with not visited in the visited 2D array. When we process the cells row by row, when we come here, the BFS traversal will be initiated. In this case, the cell at row 1 and column 1 is not yet captured and not yet visited. So the breadth first search is started from that cell. Then in this BFS function, the queue is initialized with the current vertex. So in this case 1 comma 1, and then the region is initialized with empty slice of vertex, and then the edge boolean is initialized with false. Okay, then the current vertex is marked as visited, and then we enter the for loop. So this for loop runs as long as there is an element in the queue. So in this case there is only one element, which is 1 comma 1. We dequeue that, and then we add that to the region list. Then we get the neighbors of the node 1 comma 1. So in this case, the node which is not yet captured, so basically the get adjacency list function returns the neighbor which is not yet captured. For this cell, only 1 comma 2 is not yet captured and is a neighbor, but the all other cells are already captured. So we return only this cell, which is 1 comma 2. Okay, the neighbors list has 1 comma 2. Then we enter the inner for loop. Okay, here we process all the neighbors in the adjacency list. In this case, only one cell. So we mark that as visited and then add that vertex to the queue. So now the queue has 1 comma 2. Okay, then we come out of this inner loop. Then in the outer loop, iteration 1, the current node is 1 comma 2, and the queue will now empty. And then for the 1 comma 2, we get the neighbors list. Okay, so for the 1 comma 2, 2 comma 2 is the only neighbor which is not yet captured. Okay, so that's why we have 2 comma 2 as the neighbors list. And then we also add the current cell to the region list. So we now have 1 comma 1 1 comma 2 1 comma 1 1 comma 2. These two nodes are added to the region list. Okay, so in the inner loop we process the cells in the neighbors list. So first we have only one cell, so 2 comma 2. So we mark that as visited and then add that cell to the queue. So now 2 comma 2 is in the queue, and in the outer loop we dequeue that element and we try to find the neighbors which is not yet captured, and in this case there is no node in that state, so the queue is empty. Because the queue is empty, we break out of this outer loop. Okay, then at the end we check whether the edge is false. In the get adjacency list function, whenever we see a neighbor which is out of bound, then we mark this edge as true. That means the current node is in the edge. For example, in this case the neighbor in the next row is out of bound, so we mark edge as true for this case. Okay, but for this component there is no cell which is on the edge of the board, so that's why the edge continue to be false. So because this is false, we traverse all the cells in the region list and mark them as captured. So the region list has 1 comma 1 1 comma 2 2 comma 2. Okay, so now when the BFS traversal ends, we mark all of them to captured, so all are set with value x. Okay, then we come back to the solve function. Again this for loop try to locate the next cell which is not captured and not visited. In this case the cell at row 3 and column 1. So in this case the cell at row 3 and column 1 is not yet captured and not yet visited. So we start the BFS traversal from that node. So in the BFS function we initialize the queue with 3 comma 1, and when we enter this outer loop we dequeue that node and add it to the region list. So the region list has 3 comma 1, and then we get the adjacency list. Okay, for this case the neighbor in the next row is out of bound, so we mark edge as true, and then we try to find any other neighbor which is not yet captured. All are already captured, so the get adjacency list return the empty list. Because the list is empty, this inner loop will not get executed. Then we come out, then the outer loop also break out because the queue is empty. Okay, then when we come here the edge is true for this case. Because it is true, we are not marked that visited cell as captured, so that's why it remains O. Okay, so now only this region is captured and this is not captured. That is an expected output. Next I'm going to do the time and space complexity analysis for this solution. Time complexity for this solution is order of m times n, where m is the number of rows and n is the number of columns. In order to capture the regions, we need to traverse all the cells in the grid. So we have to traverse all m by n cells. That's why the time. So this for loop basically process each cell, check each cell, and then initiate the traversal. So that's why the time complexity is order of m times n. Space complexity is also order of m times n, because we need space to keep track of whether the cell is already visited or not, and also we need a space to store the cells which are visited during the BFS traversal. So that's why the space complexity is order of m times n. Thanks for watching this video. Have a great day.